As shown in figure 7.14, if you lift an 80 pounds barrel onto a platform 4 feet high, it would require an effort of 80 pounds. But if you roll the barrel up an inclined plane 8 feet long, it requires an effort of only 40 pounds. Although the total work of 320 feet-pound is the same either way, the mechanical advantage is 1:2, or 2. Remember that the longer the inclined plane, the greater the mechanical advantage, so rolling that same barrel up a ramp that is 16 feet long requires only 20 pounds of effort for a mechanical advantage of 1:4, or 4. Mountain switchbacks are examples of inclined planes that reduce the effort of a car engine, but increase the distance the car must travel to get up the mountain. Other examples of inclined planes are gangplanks and stairs. Wedges. A wedge is a modified inclined plane and consists of two inclined planes, back to back. A wedge, shown in figure 7.15, multiplies force and changes the direction of the effort from the top to the sides. The mechanical advantage of a wedge depends on the angle of the thin end. The smaller the angle, the less force is required to move the wedge a given distance through, say, a log. At the same time, the amount of splitting is decreased with smaller angles. To find the mechanical advantage of a wedge, use this equation. MA equals length thickness. Effort. 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 For example, if you are using a wedge that is 8 inches long and 2 inches wide, then MA equals 8/2 or 4. Long, slender wedges require less effort to overcome resistance than short, thick ones. You use a wedge to split or separate objects, splitting a log, for lifting heavy objects short distances, or for holding objects in place, shims under your wood floor or around your window frames. The end of a nail is also a wedge, and as you force the nail into a block of wood, its sloping surfaces make the job a more gradual one, and you need not hammer as hard to get the nail in. Axes, needles, and chisels are examples of common wedges. Screws. A screw consists of an inclined plane wrapped in a spiral around a solid cylinder. Each revolution of the plane around the cylinder is a turn, which can run either clockwise or counterclockwise. The ridges formed by the inclined plane are the threads, and the vertical distance, from any given point on one thread to a core point on the succeeding thread is the pitch. Turnbuckles. A turnbuckle is a unique form of screw that provides leverage on both ends, which figure 7.16 shows. Normally, turnbuckles attach between two segments of rope, cable, or wire to remove slack from the line between two resistances, or between a fixed point and a resistance load. A turnbuckle has two screws, one on either end. One end has right-hand threads and turns clockwise to tighten, whereas the other end has left-hand threads and turns counterclockwise to tighten. To calculate mechanical advantage, remember that you need to take both machines into account. Figure 7.16 Turnbuckle. Jack screws. A screw can provide a tremendous mechanical advantage, because it allows you to exert an effort force over a very long distance to move the resistance a very short distance. To lift a heavy object, you must use a machine with a large mechanical advantage, such as a jack screw, which figure 7.17 illustrates. Figure 7.17 Jack screw. Jack screws combine the advantages of both the screw and the lever, in that a lever turns a screw to lift the load. A jack screw consists of two threaded surfaces. The inner surface of a hollow cylinder, the base of the jack, is threaded, and the outer surface of the internal screw is also threaded with the same pitch as the internal screw. As you rotate the lever on the top of the internal screw, the external screw and the internal screw work against each other to lift the load. Although a jack screw can lift very heavy loads, you must turn the lever that turns the jack screw many times to raise the load a very short distance. However, because there is much friction in the screw operation, the input effort is always greater than the output, and the efficiency is small. On the other hand, the effort necessary to turn the handle is small, compared to the enormous weight of the load. In the case of a jack screw, however, the inherent friction is actually an advantage, because it keeps the load from slipping when no active effort is being applied. The formula for calculating the work input and output is the same as for an inclined plane. work done in vertical lift equals work done in pushing handle. Because work is equal to force times distance, you can restate the equation like this. House weight, pitch of screw, equals force exerted on handle, circumference of screw shaft or lever. To find the mechanical advantage of a jack screw, you calculate the effort distance and compare it to the resistance distance. Because the input effort travels in a circle, the effort distance is the circumference of the circle that the lever makes, and the resistance distance is equal to the pitch of the screw. Use this formula to calculate the mechanical advantage of a screw. MA equals 2 pi r pitch. The mechanical advantage of other types of screws is the ratio of the circumference of the effort to the distance the screw advances during each revolution. Remember that the length of the lever arm is the radius. To find circumference, you use the formula 2 pi r is roughly equal to 3. 14. Be sure all your quantities are consistent. If you are using inches to specify your pitch, you should also use inches to specify circumference. In the case of a jack screw, if a house weighs 4,000 pounds, the pitch of the jack screw is 0.250 in, and the length of its handle is 12 inches. Find the amount of effort required to move the lever by substituting in the values in the formula for work. Resistance times pitch equals effort force, circumference. For 1,000, 0.250 equals F times 2p, 12.0. 1,000 pounds equals 24 pi F. And F equals 1,000/24, 3.14, or 13.3 pounds. So you need a force of 13.3 pounds to turn the handle on the jack to begin to lift the 2-ton house. To find the mechanical advantage, divide 4,000 pounds by 13.3 pounds, for an MA of 302. Screws can hold things together, as with pieces of wood or metal. A jar lid, a piano stool, and a vise are other examples of a screw. In addition, screws can lift heavy objects or move objects by a precise amount, such as making delicate adjustments to tools and machines. Gears and other simple machines. Gears are a form of wheel and axle that have teeth around the edge, instead of a groove for a rope. As with a wheel and axle, a gear is a form of lever, wherein the arm of the lever is the radius of the gear, and the center of the gear, or the shaft, is the fulcrum. Gears can change the effort direction, and can increase or reduce a force, or the distance over which that effort is applied. Gears can be a toothed wheel or a toothed cylinder or cone that meshes with another gear to transmit motion and force. In any pair of gears, the larger gear rotates more slowly than the smaller one does, but with greater force. By meshing gears of 2 different diameters, you can vary both speed and torque between the 2 shafts. 2 or more gears in a single effort constitute a gear train. Gear trains reduce or increase the speed or torque output of a rotating system, or change the direction of the output of a system. The first gear in the train is the driver, and the final gear in the train is the driven gear. Any gears between these two are called idlers. Every successive gear in the train reverses the direction of the previous gear, meaning that if the driver gear is turning clockwise, the next gear in the chain will turn counterclockwise, and the third gear will again turn clockwise, and so on. An idler gear does not alter the gear ratio between the driver and driven gear, but it conducts effort in the same direction and speed as the driver. However, if the idler gear speeds up or slows down the gear speed, then it is a gear differential, it differs the gear speeds. In addition to these, you should be familiar with several gear types, discussed in the following paragraphs. Figure 7.18 shows the different types of gears, and the list that follows discusses those types.